Hello and welcome to Office Hours, our first program of 2022. Happy New Year. Hope you and yours are all staying safe and healthy. My name is John Kowalski. I'm part of the marketing team here at Vic Gardner and will be the moderator for today. If you're unfamiliar with our Office Hours format, it is essentially a shortened presentation, 20, 25 minutes. And then the rest of the time is yours to answer any questions, challenges you may be having at your own facility, or anything on your mind we can help with. So if you do have a question, please log it in the chat box in the bottom right-hand corner of your screen, and we'll get to them in order immediately following the presentation. So with that, I'm going to turn things over to our expert, Senior Applications Specialist, Mr. Corey Cohen. Corey? It's all yours, sir.
Thank you, John. Welcome, everybody, to our first office hours of 2022. Today's topic is color theory, and that is a pretty broad topic. So I'm going to give you sort of the bare bones basics, just the fundamentals, and then let you guys guide the discussion. And you know, as John mentioned, just let us know what you want to hear about, and we can delve into it. So let's get started. So color perception. We talk about the three components of color perception, and this is important when it comes to color measurement, because in order to quantify color, in order to measure it in a scientific way, we have to understand how we see color, how we perceive color. So it's important to understand each of these three components: the light source, object, and the observer. So starting with the light source, light is part of the visible light is part of the electromagnetic spectrum. So this encompasses all sorts of things like X-rays and microwaves and radio waves. It's all the same stuff, just different wavelengths and frequencies. So this particular range of wavelengths from about 400 to 700 nanometers, that is what we call visible light, because it's visible to us. None of the other EM waves are visible to us, only this very small range in the electromagnetic spectrum. And if you go into the shorter wavelengths, you go into UV, which is invisible to us again. And if you go to longer wavelengths, you get into IR or infrared. UV is ultraviolet, IR is infrared, and they are both invisible to us. So when it comes to color measurement, we're only going to focus on what we see, because it's only the visible wavelengths that are affecting how we see color. And that's this range between 400 and 700. So the specific wavelength of the light determines the color. So at the very short end, the 400, 420, 440, we get some violets and then blues. And then as we get longer and longer, we get into the greens, yellows, orange, and red. So each wavelength has its own distinct hue. And if you mix all of the colors, all of the wavelengths of light together in approximately equal amounts, you get white light. And so white or whitish light sources generally contain all of the visible wavelengths in some amount. And so here we have what we call the standard illuminants. And these were developed by an organization called CIE, which is a big name in color measurement. It's an organization, it's in French, and I can never remember the French name, but translated it translates to International Commission on Illumination. So they standardized these illuminants, which are just descriptions of common light sources we come across in everyday life. And so what we're seeing here, these curves, let me activate my pointer. So these curves we're seeing here, these are called spectral power distributions, and it tells us the relative amount of each wavelength in these various illuminants that represent these different light sources. So for example, we have D65, which is meant to represent the spectral power distribution of north sky daylight. And so we can see that's a pretty even white light source. If you have A bulb that represents 6500K light. That's what the 65 stands for. 6500K is the color temperature. And so those are always very, very white light sources. It's very, very even light source and slightly bluish, which actually makes light sources look a bit whiter. And then we have the A illuminant, which is meant to represent a tungsten bulb. So this is what we call the incandescent illuminant. And if you're familiar with tungsten bulbs, or if you remember tungsten bulbs, because we don't really see them around anymore, they tend to have like a yellowish, orangish, what we would call a warm hue to them. And that's because if you look at the spectral power distribution, you can see that they're heavily weighted towards the longer or the warmer wavelengths. So this is why we get that warm, yellowish, orangish glow with tungsten bulbs. And then this is an example of one of several fluorescent illuminants, which they tend to have these spikes in the spectral power distribution, which is caused by that fluorescent effect. And the whole point of this, the reason we need different illuminants, we need to simulate different light sources, is because colors look different under different light sources or different illuminants. And so we need to be able to simulate different ones so we can make sure that our colors match and that they look like they're supposed to under various lighting conditions. One component when talking about light sources, we can also talk about a phenomenon called metamerism. And metamerism is where you have two colors that may match under one light source, but not under another. And so this is another reason why it's important to sometimes test your material under different light sources. Because as you can see here, this these sample colors, these cups here, these orange cups, under the D65 illuminant, under daylight, they're a good match. But under the tungsten illuminant, under a tungsten bulb, they would not be a good match. And the reason is because their spectral curve, their spectral reflectance curve, the amount of each wavelength reflected off of these colors is different. So we see these spectral curves are different. And now it is possible for different spectral curves to produce the same color under a given lighting condition. But if you switch lighting conditions, as for example here, we've gone from D65 to the A light source or illuminant, they suddenly don't match. And that's called metamerism, when colors match under one light source but not under another. So that was the first component of color perception, the light source. So the next one we're going to talk about is the observer, which is us. So we have eyes that can detect light, that can detect color. And these eyes are made up of a collection of different types of cells. And it's these two types of cells in particular, the cone cells and the rod cells, that allow us to see all the different colors we can see. So the cone cells, those are our color detectors. And so they have three flavors of cone cells. We have green cone cells, red cone cells, and blue cone cells. And they're each responsible for detecting a different range of wavelengths. And then we have the rod cells, which are lightness detectors. So they pretty much just detect how light or dark something is. And we refer to them as lightness detectors at night because at night or anytime you're in low lighting conditions, sometimes there's not enough light to activate those cone cells. And at that point, they just shut off and we're not using them anymore. We're only using the rod cells. And that's why under low lighting conditions, we typically see things in shades of gray. We can't see color. So in order to fully understand the observer, how we see color, this experiment was designed to ascertain the precise sensitivities of those different cones in our eye. And so the way this this experiment went was you would have an observer, a test subject, behind a masking screen. And this test subject could only see through a thin slit. And that was important. I'll get to why in the next slide. But so this test subject is looking through the slit onto a screen. And that screen is partitioned into top and bottom. And on the bottom would be projected a colored light source. And then on the top would be projected the three primary colors relating to those three cones in our eye. And so it was the test subject's objective to adjust the power level or the intensity level of those three colored lights on the top until the mixture of those lights projected on that screen matched the light source projected on the bottom part. And so by repeating this experiment with different test subjects in many different colors, we were able to ascertain the sensitivities of those cones, which we call the observer functions. So the first set of observer functions was developed in 1931, and that was developed using a 2-degree field of vision. So this is why the test subject could only see through a narrow slit in that screen. That was on purpose because it was believed, first of all, it's important to control the field of vision just for consistency. But such a narrow field of vision, the 2-degree, was used because it's believed that the cones in our eye are more concentrated towards the center of the retina, whereas as you go further out, you get into more of those rod cells. And so they wanted to isolate the cone cells as much as possible, and that's why a narrow field of vision was chosen. But it was found that that doesn't agree. Those observer functions don't agree as well with color viewing as we'd like them to. And so that experiment was repeated in 1964 with a 10-degree field of vision, so a much wider field of vision. And the way you can visualize this is if you hold a quarter out at arm's length, that's approximately a 2-degree field of vision. If you hold a tennis ball out at arm's length, you're looking at about a 10-degree field of vision. It was found that 10-degree observer, those functions do correlate a bit better with color viewing. And so that's today pretty much exclusively used, the 10-degree observer. There are certain special applications, legacy calculations that use the 2-degree observer, but for the most part, we stick with 10-degree. And so this is what those observer functions actually look like. And here we're seeing the 2 and the 10-degree observer. So the 2-degree are represented by the solid lines, the solid curves. And so we can see that the blue cone has maximum sensitivity somewhere around 450 nanometers. For the green, it's around 550, and for the red, it's a little over 600. And if we switch to the 10-degree observer, which are the dotted curves, we can see that we're getting a bit more sensitivity in each area, which is why this correlates a little better with how we typically see colors in everyday life. So we've talked about light source, we've talked about observer. Now we just need to know what's going on with the object. So when light hits an object, there are a few things going on. One thing that's going to happen is you're going to get direct reflection off of the surface, and that's the gloss reflection. So glossy surfaces are going to have a stronger gloss reflection, or what we call the specular reflection. And that light that's bouncing off of that surface, that gloss reflection, is not undergoing any interaction with that material. It's just bouncing right off the top. So the spectrum, perhaps not the power or the intensity level, but the spectrum of light that you're seeing reflected off is going to be the same as the light source itself, because that light is not being modified at that specular angle. But what's also happening is some of that light is going to penetrate the surface. It is going to interact with the chemistry of that material, specifically the pigmentation in the material. So for example, you can see here, this is an orange pigment, and that orange pigment is going to selectively absorb certain wavelengths. Specifically, it's going to absorb most of the shorter wavelengths, the blues and the greens, and it's going to reflect more of the yellows and oranges and reds. And so the mixture of reflected colors is going to be orange. And then when that light reflects off of those pigments, that light is going to be diffused, which means it's not going to reflect off in one direction. It's going to reflect off in all directions. And so this is why when we measure gloss, we measure it at the specular angle, the opposite angle of the light source. But when we measure color, we always measure that at a diffuse angle. So here again, we just have another similar representation. So we have the incident light source, and you can see that this is a mixture. It's white light, so it's a mixture of all different colors. And that specular reflection has that same spectrum, so it's still a mixture of all different colors. There's no pigment interaction there. But with some of that light, we are getting the absorption, we are getting pigment interaction, and we are getting diffuse reflection. And so again, this is where color would be measured in the diffuse angle, usually normal to the surface. And so when we measure a color, when we use a color instrument to measure a color, what it's actually measuring is the spectral reflectance curve. It's measuring how much of each wavelength of light is being reflected by a color or a material rather than absorbed. So for example, here at the top left, we have a blue color, and so it's reflecting a lot of blue wavelengths and not much else. Red is reflecting, of course, red wavelengths and not much else, and so on and so on. So illuminant, object, observer. And so we need all three. We need the quantification of all three of these in order to calculate those color scales. So the spectral reflectance curve, this is what a spectrophotometer actually measures, whereas the illuminant and the observer functions, those are just calculations. That's just a set of numbers that are in the instruments that are used once you measure the spectral reflectance curve. Those numbers are then used to calculate color values based on, again, the spectrum of the light source as well as the sensitivity of our eyes. And so we get color scales such as XYZ. Those are referred to as the tri-stimulus color values. And those are sort of a direct representation of how much light is being seen by each of those cones in our eye. But it's not really a very intuitive color space. So we want to convert that into something that's a little easier for us, a little more intuitive to understand. And generally that would be the LAB system. So this is something else that was developed by CIE, the International Commission on Illumination. And this is a three-dimensional coordinate system where you can describe any color as a point in this three-dimensional space. So for LAB, we have three axes. We have the L axis, that's the vertical axis, and that's for lightness. So the higher the L value, the lighter your color. And then we have the A value, which is for red and green. So a positive A value indicates that there's red in the color. And a negative A value indicates that there's green in the color. And this is based on what we call opponent color theory, which is where red and green are considered opposites. And so you can move back and forth on this line to say that you have more red or less green are exactly the same thing. But you can't have lots of red and lots of green in a color because they're opposites and they would cancel each other out. So you get one A value, and then you get the B value, which is for blue. A negative B value is indicates blue in the color, and a positive B value indicates yellow. And again, those are opposing colors. So the more yellow you have, by definition, the less blue, and vice versa. So you describe a color by giving these three values, L, A, and B. Now there is an alternate way to describe colors, and that's with LCH. So this is the same color space. It's just a different way of describing these colors using polar coordinates rather than Cartesian coordinates or rectangular coordinates. So here the L value is the same, it's still the vertical axis. But instead of having A and B, we have C and H. So C tells you how much chroma there is in the color. So that's, we might use words like how deep a color is or how saturated a color is. It's how much color there is in the color. So like a gray or white or black, those are neutral colors. They have no chroma. Whereas like a scarlet red or I don't know, a lime green, we would say those are very chromatic colors. So those would have a high C value. And then we have the hue angle, which actually describes the hue of the color, red, yellow, green, blue, as an angle off of the positive A axis. Right? So you start at positive A. Positive A is a hue angle of 0 degrees. So 0 degrees means a red color. And as you go counterclockwise from there, that angle goes up. So the yellow axis, the positive B axis, is 90 degrees. The negative A axis is 180 degrees, and negative B is 270. And so we can describe the hue as a as an angle in this sort of AB plane. I believe we have an example. Yes, so here we have a color with an L value of 58, so kind of a medium light color. The A value is positive 30.41. So that's a good amount of red. And it also has a B value of positive 36.26. So it's a good amount of yellow also. So we have a medium light color with lots of red and lots of yellow. So this would be a fairly chromatic orange color. And so when we measure colors, typically we're not too concerned with what are the absolute LAB values. What we want to know is how much does this color differ from this other color, our standard or our target color. Typically we're going to have some color we're trying to match, and we want to see, or we want to make sure that that color that we're producing matches that target color. And so what you do is you measure the target color, which we refer to as a standard, and you measure the production color or your sample color, and that's called the sample. And then you can take the differences. So you can calculate the difference in the L value, and that will tell you how much lighter or darker the sample is than the standard. You can calculate the delta A value, which tells you how much redder or greener the sample is than the standard. And you can calculate the difference in the B values, which is how much yellower or bluer the sample is in the standard. And so to do that, you just take the, for example, to calculate delta L, you take the L value of the sample and subtract the L value of the standard. And now, so generally when it comes to, QC type work, the fewer numbers we can look at, the better. So we don't want to look at 3 numbers if we can just look at 1 number. And that's typically going to be this value here, the delta E. So the delta E is what we refer to as the overall color difference, and it's just a single dimensionless number, meaning it's not positive or negative. It's just a number. I guess you could say it's always positive. And that number describes just the overall difference between 2 colors, and it takes into account the L, the A, and the B. And so you calculate it by this equation here, the difference in the L value squared, plus the difference in the A value squared, plus the difference in the B value squared, and then square root the whole thing to arrive at the overall color difference. And so what this actually is just the distance formula in this CLAP space. So if you were to plot 2 colors, 2 sets of LAB values in this space and just measure the distance between them, that's all this delta E is. It's just the distance between these 2 points in this CLAB, CIE LAB color space. So that's all I got. Hopefully that was enough to sort of get the engine in gear, and you guys can produce some questions for me and decide where to take it from here. I've included a few possible topics for discussion, and so go ahead and enter any questions you have into the chat box, and we'll get started.
Yeah, thanks, Corey. Great stuff as always, and topics for discussion are always good. Like Corey mentioned, if you have a topic, something on your mind, some challenge at your own facility, just enter it in the chat box, and we'll either take care of it there, or if needed, I'll unmute you, and we can go from there. So when you get into color theory, Corey, are there like high-level questions that you always get every time you're talking this topic?
John, you ask me that question every time, and for some reason, never prepared. I guess one that comes up a lot is 45-0 versus sphere. A lot of novices to color measurement might think that a color measurement device is a color measurement device, and that it's all going to give you the same answer. And the truth is, every color measurement device is different. Calculating color, quantifying color, as you've seen, is pretty complex business. And so no two color instruments are really ever going to give you the same answer. But in particular, there are two types of color measurement instruments, or instruments we could say for solid color, which means we're not dealing with any special pigments like metallics or pearlescence, color changing pigments. We're just talking about absorption pigments, just the everyday pigments in your clothing and the various colored plastics you have around the house and things like that. And so the main difference between 45-0 and sphere is that 45-0 sees color as we see it, and sphere ignores any surface effects and only measures the pigmentation. And I should back up a second to explain that. So gloss makes us see color different. So typically glossier surfaces appear darker and more chromatic to our eye, even when the pigmentation is exactly the same. So when you're selecting a 45-0 or a sphere instrument, you're selecting whether you want to see or what you want to measure the color as we're seeing it, where the gloss is going to influence how we see the color, or the texture, or the texture will influence how we see the color, I mean, or the sphere, where we're only measuring the pigmentation and we don't care how the surface is affecting our color vision. So if you'd like me to go a little deeper into that, I can do that as well.
That was actually a question, our first question from Joel. Joel, did that answer your question, or do you want him to dig a little deeper? You can just put a nod either way in the chat function. Denny asked if we can get the slides. We'll send out the recording of it, and that will be coming to you directly after this is done. You'll get a link to that recording there. Let's see, Caitlin, I was wondering if there's an ideal light source to view an object at, or is that highly dependent on the actual color of the object?
So the ideal light source is the one that you will actually be using, or where the product will actually be viewed under. So if you're producing products that would be used outdoors, typically you're going to want to use a daylight source. If you're going to be producing products that might be sold in a department store, department stores typically use fluorescent lighting, and so it's good to test that color under fluorescent lighting to make sure that those colors are going to look good when consumers go to view them inside that store. And really, with these instruments, you can test under multiple light sources at the same time. So it's not like you have to take multiple measurements. You can actually select a few light sources and see how the color numbers will differ, or how the color differences will differ if you might be dealing with some metameric colors. So I will say that D65, the daylight illuminant, is by far the most commonly used illuminant for QC. But it does pay sometimes to think about your product and where your product is being used, where your product is being viewed or purchased, and make sure that it looks good under those light sources as well.
Good. Good. Thanks, Corey. Question from Mike. Spin versus spec values.
Okay, so let's this is related to 45-0 versus sphere, so we're just going to go all out and just go ahead and knock this one out.
We're getting deep now. That's good. There's a steady flow of questions coming in, so you guys are on fire this year so far. That's great. Before we get that up.
All right, I'm reaching into my own pocket for some presentations, so I'm going to go ahead and share my screen if I can remember how to do that. There it is.
Yeah. Yeah, keep those questions coming too. We have about 4 or 5 in the queue, but we have plenty of time left.
Okay, so here we have 2 painted panels, and the entirety of each panel was painted with the same color. The reason you're seeing differences in the top and the bottom of these panels is because half of each panel was coated also with a glossy clear coat on top of that paint. So that clear coat contains no pigmentation. It's not affecting the actual color, but it is affecting the gloss. It's making the surface much glossier looking. And so we can see that the glossier side of each of these panels looks darker. Gloss makes colors look darker to us. And in the case of this red color, which is a chromatic color, remember the black has no chroma, but the red has plenty of chroma. It's a very chromatic color. And not only does the glossy side look darker, it actually does look redder. It looks like it has more chroma. And again, that's only an effect of the gloss. That's not a difference in the pigmentation. So the glossy part looks darker and more saturated despite being made of the same colored material. So both color and gloss influence our visual impression, how we see colors. So we have these 2 instruments. This is the 45-0. And so it's called 45-0 because the light source is at a 45-degree angle. And we can see that this is a sort of cone of light. The light's coming from all directions, but it's all hitting the sample at a 45-degree angle. So this is what we refer to as circumferential illumination, but it's still 45-degree illumination. And then the detector is at 0 degrees or normal to the surface. Because again, remember, we always measure color at a diffuse angle. We wouldn't want to measure it at one of these opposite 45-degree angles. So for this instrument, for the 45-0 geometry of spectrophotometers, differences in gloss and structure do lead to measured color differences. So this one measures color as we see it. So we're seeing the glossy part of the panels as darker. This instrument is going to measure it as being dark, and we'll see that in a minute. Okay, then we have sphere, and this is called sphere because it has what we call an integrating sphere inside it. It's a hollow white coated sphere. It's coated with a diffuse white coating. So in this case, instead of illuminating the sample directly, the light source is shining light into that sphere, and that light is bouncing all around and becoming diffuse before hitting the sample. So whereas with the 45-0, that's a directional light source. It's coming from one angle. Here with the sphere, it's diffused light. It's coming at all angles. And the detector is positioned at 8 degrees off the normal. So this is often referred to as D8 or diffuse/8 degrees. And so for this type of instrument, we refer to this as sphere spin. specular included. You'll also see it referred to as SCI, specular component included. They're the same thing. With this one, differences in gloss or surface structure, surface texture, do not lead to measured color differences. This one is going, because of the diffused light source, it's going to ignore those surface effects, and it's going to just measure the pigmentation. So differences in gloss and structure do not lead to color differences. And then we have sphere specs. And so this one, it was made to try to simulate a 45-0 instrument because color instruments are expensive, and they used to be a lot more expensive. And so if someone needed both a 45-0 and a sphere, that was, of course, a very expensive prospect. And so the sphere specs was developed so that you could have one instrument, a sphere instrument, that can measure both like a sphere and like a 45-0. And so this is what sphere specs was developed for. And specs stands for specular excluded. You'll also see SCE, specular component excluded. And so this one just introduces a gloss trap that eliminates this light from being specularly reflected into the detector. So it's eliminating the specular reflection, and that causes it, excuse me, to act more like a 45-0. So here, gloss differences do lead to color differences. It has good correlation to 45-0 on high gloss surfaces, but not so great at lower gloss levels. So here we have some examples. We've measured both sides of that black panel with each type of instrument, and we can see the differences in the color values. So if we look at the 45-0, 45C, the C stands for circumferential. So this is a 45-0 instrument, the one that measures color as we see it. And so when it measures the glossy side, it measures it as being darker than the matte side, or the less glossy side, just as we see it. Similarly, with the specs instrument, that's also going to measure the two sides being different, whereas the spin ignores that surface effect, that surface gloss. It's only measuring the pigmentation, which is the same, and so it's going to see these two, the two sides of this panel as being essentially the same. Similarly, with this, the red panel, so the 45-0 is seeing some differences between the two sides. It's, again, the glossy side is being measured as darker. The L value is lower. It's also measuring it as being more chromatic, higher A and B values. Because this is a chromatic color, it is going to see differences. Again, with the specs, that's seeing something similar. But the spin, again, does not care about that surface gloss, and it's only measuring the pigmentation. So it'll measure them as being essentially the same.
Nice.
And that's what I got on 45-0, sphere, and specs.
Nice. Appreciate it, Tori. Another question here. How do you measure color of a coating containing metallic pigment?
Okay, so that requires a multi-angle color instrument. And the reason for that, hold on, please. I think I have to.
Another presentation in your back pocket there?
Yep. How about
we'll get to this here. Okay. And more questions keep rolling in, so that's great, folks.
Okay. Are we seeing this, John?
Yes, all good.
All right. So for colors with metallic pigments, you need to measure them at multiple angles. And so this is our Bic Mac, our multi-angle color instrument. It has 1 angle light source, 1 angle illumination, and 6 angle detection. The 15, 25, 45, 75, 110. Oh, it's not shown here. There's another angle, the -15. I guess they're building up to that in this presentation. Anyway, so 6 different observation angles, 6 different measurement angles. And the reason for that is because with metallic pigments, typically you're going to have some light dark flop. And that's when a color will look lighter or darker depending on the observation angle, because of the way that light is bouncing directly off of those very, very bright, very reflective little bits of metallic pigment. The angle you're observing at, the angle you're standing at when you observe something like this, is going to affect how light it appears. Typically, the closer you are to the specular angle, the gloss angle, the lighter the color is going to look, because you're getting more direct reflection off of the metallic pigments at those angles. So, for example, losing my voice. That wasn't the example. So, for example, we have a solid green color. Solid meaning only absorption pigments, no metallic pigments, or what we call effect pigments. And if we measure this color at 5 or 6 different angles, whatever, we're going to get essentially the same answer at all angles. It's going to look pretty much the same, and that's why this or these spectral reflectance curves that we're seeing for these different angles are pretty much right on top of each other. It's seeing the same color at all angles. But now we add some metal pigments, metallic pigments, some aluminum flake or whatever into this green color, and all of a sudden we're experiencing some significant light dark flop. So we can see from these curves, they're all a similar shape. So we know that the hue, that green hue, is going to be pretty similar no matter the observation angle. But these curves are at different levels, which means that the lightness is going to change as we go. So at this near specular angle, the 15-degree off of the specular, we're going to see a lighter green color. And as we go away from that angle, it's going to get darker and darker. And then we have this example of a metallic silver. This has typically more metallic pigments, and it's going to exhibit more light dark flop. And so we can see this is a neutral color, so it's a pretty flat curve, but the overall level of these curves are changing drastically. Look at the y-axis here, the percent reflectance of this metallic green versus this metallic silver. So this is silver is going through some pretty extreme light dark flop, and so it's necessary again to measure this color at multiple angles to make sure that it matches the standard or the target, not just at one angle, but at all observation angles.
Good stuff, Corey. DJ, I'm sorry if I'm mispronouncing your name. Let us know if that answers your question, if you could. Next one here, please share any suggestions to help when measuring fluorescent colors. This is from Brittany.
Fluorescent colors. My first suggestion would be use the Spectra 2 guide. Because, and I'm not just saying this, but it truly is the most accurate instrument for fluorescent colors out there. And I'll try to show you why. It's a little mathematical, so I sometimes have a little trouble explaining it, but I'll try to show you.
In the presentation. I love that game. did answer your question, DJ. Thank you for letting us know. Glad it helped. All right.
Nope, that's not the one I wanted.
We'll click on the. Go ahead.
Okay. First of all, what is fluorescence? Fluorescence is when a material, a molecule, whatever, absorbs light at a given wavelength and re-emits it at a longer wavelength. So I won't go into the specifics of that, but it's basically just converting light into light of longer wavelengths. So it can convert ultraviolet into blue light. Remember, ultraviolet is invisible to us, but once it goes through fluorescence, it can come back as blue light, which is visible. It can take blue light and convert it into green light, green to yellow. It always goes from shorter wavelength to longer wavelength. And so this throws sort of a wrench into the works when it comes to color measurement, because we have to account for that, particularly when it comes to different light sources. So we have this instrument, our Spectra 2 guide, which is not only a spectrophotometer, it is actually a handheld fluorimeter. A fluorimeter is an instrument specifically for measuring the fluorescence in a material. And so what it does is it has these 12 individually colored LEDs, these narrowband LEDs ranging from 360 to 660 nanometers. And it individually shines light. Each of these LEDs individually shines light on the sample, and then the instrument quantifies how much light, how much fluorescent light is coming back. So it's not measuring reflectance like a spectrophotometer would do. It does that also, but just for this fluorimeter portion, this fluorimeter function, it's only measuring the light that's reflected back at longer wavelengths. So it's only measuring the fluorescently re-emitted light. And so you get these fluorescence curves that show you when you shine light of a given wavelength on it. This is the light, the fluorescent light that bounces back. But what it also does, it incorporates that data into the color values. So let's get past all of this. Okay. So this is where the Spectra 2 guide differs from other color instruments that can also sort of measure fluorescent colors. The thing is, each of those other color instruments, their light source is xenon flash or tungsten or whatever, and there'll be some UV component to that light source. And so it can measure that as those color instruments shine light on a sample. Of course, if it's a fluorescent sample, fluorescence will happen and it will measure that color. But I think I'm getting a little lost in the weeds here. So, okay, let me back up a bit. When we measure color, we measure a spectral reflectance curve, which means that when you shine a certain amount of light of each wavelength on a sample, we're measuring what percentage reflects back. So we get a spectral reflectance curve describing the percent reflectance at each wavelength. But that spectral curve is independent of any illuminant, right? We're just getting reflectance data. We're just learning about the material itself, not how that material looks under a given light source. In order to do that, we have to apply the appropriate illuminant to it to calculate what that color would look like under each illuminant. So that's why whenever you take a color measurement, you always have to specify the illuminant. You can't take a color measurement without the illuminant. So you have to modify that spectral curve by these illuminants in order to arrive at the specific set of color values for that illuminant. And remember that set of color values will be different for each illuminant. The problem with most color instruments is that, so you're getting two sources of data with fluorescent colors. You're getting the light that is reflected back at the same wavelength and the light that is reflected back at longer wavelengths. And most color instruments cannot parse out, cannot separate that fluorescently emitted light from the reflected light. And so the color values you are going to get with fluorescent colors will be heavily dependent on the actual light source in those instruments rather than the selected illuminant. Whereas the Spectra 2 guide, because it can separate out those two sources of light, the reflected light and the emitted light, it can modify it appropriately for whatever illuminant is selected. So rather than just getting fluorescent colors based on whatever light source happens to be built into that instrument, you can get much more accurate color values for fluorescent colors because it is calculating it specifically for that illuminant in a way that instruments without a built-in fluorimeter can't do.
Right.
Hopefully that makes sense to at least one of you.
Yeah, nicely explained, but it is complex. So you may need to review this recording a couple times to get through that. Let's see, question from Michelle. In the measurements, are there any assumption about the refractive index in which the pigmentation is suspended in? How does refractive index of a material affect color measurements?
Interesting. So I will say that refractive index has an influence over gloss measurement. It is typically recommended that you only compare gloss measurements on materials of the same or very similar refractive index because that can affect the gloss value you get. As far as color, to my knowledge, refractive index doesn't really affect color measurement, I don't believe.
Okay. Hope that answers your question, Michelle. Corey, can you put up the last slide of the office hours presentation with your email? If anyone has any questions after the fact, they can reply to any of the automated marketing messages and we can route them to Corey, or you see on your screen Corey's email address there. Feel free to write him directly if there's any questions you have or anything he can help you with. Next question here. Do you have an instrument that has the capability to measure or detect the percentage of haze of a color panel after xenon exposure?
The percent haze, okay, of a color panel. So I believe we're talking about a solid colored object, not a transparent object, because there are two types of haze, haze for transparent materials and haze for reflective materials. We do have an instrument that can measure reflection haze, and it is called the haze gloss. It's a benchtop instrument. It measures reflection haze at 20 degrees, which is the standard angle for haze. And it also measures 3-angle gloss.
Okay. Good. There you go. Next one, Caitlin. Does texture, such as sand, change the way color is viewed?
Absolutely, yeah. Texture, similarly to gloss, is going to affect the way light bounces off of surfaces, especially when it's a directional light source. So you're going to get similar effects with texture as you will with gloss. Although I guess you could say texture would sort of be opposite to gloss. The glossier something is, the darker it's going to look. The more texture something has, typically the lighter it's going to look to you. And again, the 45-0 will measure it the same way you see it. It will measure lighter color values due to that texture. Whereas again, the sphere spin instrument we'll ignore that and just measure the pigmentation.
Great, great. Next one from Mark. What about LED light source used in homes or stores for viewing color?
Oh yeah, so yeah, we've gotten that question a few times over
Yeah,
the months and
yeah, we
years.
have.
So there are LED light sources, or I should say LED illuminance. CIE has developed a collection of I guess, commonly used LED illuminance to match up with the light sources that are increasingly going in department stores and things. I think Walmart is a driver for this. They're putting LEDs in all their stores. Um, I haven't seen a color instrument yet that has these light sources built in. And the reason for that is because no one is asking for them yet. This type of thing is driven by industry, particularly Bic Gardner. We are very responsive to the needs of our customers and work closely with our customers to implement whatever calculations or measurements they want to see in our instruments. But the fact is, no one has really asked for it yet. No one has specified it. As soon as some important specifier specifies that they want to get color measurements under LED illuminance, that's when they will be added into color instruments.
Sure. Follow-up question to that. Is CIE working on LED model of viewing? That's probably right.
Is CIE working on what?
An LED model of viewing. You know, CIE is doing anything with LEDs?
Um, LED model. Oh yes. Yes. This they do have LED illuminance. Yeah. This is what I was just talking about. So they have developed illuminance, spectral power distribution curves for LED. They just haven't been widely implemented yet.
Due to not being written in any standard. Yes, but I'm sure it's coming. Okay, Mark, that answer your question there? Next one here from Mike. What is the spectral distribution curve of a spectrophotometer light source?
It depends on the spectrophotometer. We use white LEDs with yeah. So the truth is, it doesn't really matter what the spectrum. I mean, excluding that example of fluorescent colors that I was just talking about. If we're talking about non-fluorescent colors, it doesn't really matter what the spectrum of the actual light source is, because that can be calibrated. Whatever the spectrum is, it can be calibrated. The important part is to have enough power at each wavelength to get an accurate measurement. So if you have a light source, for example, if you might be using an instrument with a tungsten bulb that has very low emission in like the blue range, those percent reflectance measurements you'll get in that range aren't going to be perhaps as precise as you might get with a light source that has more power in that range. So it doesn't really matter what the spectrum is. You just need to be able to see enough power at every wavelength. And so typically in older instruments, you will see tungsten bulbs and xenon flash. And so whatever the typical spectrum of those is, that's what you'll see.
Okay. Well, thank you, Corey. And like we made it just in time here. We got through all the questions. If anyone thinks of a question after the fact, feel free to email Corey directly. His email is on the screen there, corey.cohen@altana.com, or you can reply to any of the marketing messages you get from us, and we'll route it to Corey. Also, stay tuned. Next month's office hours, what goes better with a color theory than appearance theory? Yep, next month. February 16th, same time, 2 p.m. Eastern, we have an office hours on appearance theory. So you'll receive invites to that, and if you want to register and join us then. But we appreciate the time you've given us. Hope you learned something. Have a great day, and stay safe and stay healthy. Thanks again, Corey.
Thank you. Thanks, everyone.